Hey guys, Mr. B here, and in this video we're going to be going over the chapter 11.1 notes on distance and displacement. Alright, so this is the first section of the chapter, and in this chapter we're going to be talking about motion, and kind of leads us into a lot for this first half of general science on Newton's laws of motion and other things like that. So first off, we're going to talk about a frame of reference. So what is a frame of reference? So when we talk about things that are moving, in order to describe moving objects, we need to have a frame of reference. Okay, now as for what a frame of reference is, a frame of reference is usually going to be a bunch of objects that are not moving in relation to each other. So, the most common frame of reference that you use on a regular basis is the ground or planet Earth and things that are attached to the ground, right? So, trees are attached to the ground, trees are not moving. Signs or buildings are attached to the ground, they're not moving. Your house and your desk is attached to the ground, therefore it's not moving. And then when something were to come around that isn't attached to the ground, you would go, oh, that thing is moving, right? Look at that car drive down the road. Look at that bird fly through the air. Look at that person running along the ground. They're not attached to the ground, therefore they're able to move, right? So a frame of reference is sort of like the backdrop that you use to determine whether something is moving or not, okay? In this picture here, they show two guys both watching a car go down the road. One of them is going, oh, hey, that car is going to the left. And the other guy's going, no, that car is going to the right, based on their frame of reference. And neither of them is wrong, of course. They're both right. It just depends on what frame of reference you use or what perspective you kind of view it from. Now, because motion can be viewed from these different frames of reference and different perspectives, we say that all motion is relative, okay? So what that means is that when you're describing a moving object, you need to understand what frame of reference you're describing it from and understand that there could be other ways to describe it moving other than just the way that you are, right? So here's a prime example. Imagine that there's a train going down a railroad track and it's going past a station or a platform where all these people are like waiting, right? And so as this train comes flying past them, they're going to view the train, going 60 miles an hour as it goes when it whizzes past their face. And all the people that are sitting inside the train may be looking out the window. They're going to see their faces fly by them at 60 miles an hour. But for the people that are in the train, sitting in their seats, they're probably going to look at each other and go, well, we're not moving 60 miles an hour. I'm sitting in my chair. I'm not going anywhere. You're the one outside the window who's moving past me. I'm sitting still, and you're whizzing by me. So you're moving. I'm not moving. And again, it's a weird way to think about it, but both are correct, right? I mean, the train is certainly going down the track at 60 miles an hour from one perspective. And at the same time, the people in the train sitting in their seats are not moving, and the things outside the window are moving from their perspective. So having a frame of reference is really important because it basically allows us to describe in a very clear and relevant manner what is happening, okay? As well as changing your frame of reference can also be helpful if you're trying to describe or explain something in particular, okay? So, anyway, there are some questions here which we're not going to answer. There's a video of me going over those. You can go watch that on your own. But this video is just going to be going over the information. So let's continue here. All right, so now other than a frame of reference, of course, let's talk about how do we measure length and stuff like that when we talk about moving objects. So the first thing we'll mention here is distance. Distance is the length of a path between 2 points. It does not have to be in a straight line, okay? This is the key thing with distance. So distance is the length of a path between 2 points, but those 2 points do not have to be a straight line from each other, right? So, imagine if you've ever driven down the road and you've seen signs that tell you like how many miles to the next town, right? Like 20 miles to Watertown. They're not telling you it's 20 miles in a straight line. They're telling you it's 20 miles if you follow this road, which probably has to curve around some trees and there's bends and stuff in it, but it's 20 miles of road you're going to drive on. If you could just go straight there, like through the woods, it's probably less than 20 miles. So understand that distance is the whole path that you have to take. A lot of times it is not a straight line, okay? And there are different units, of course, we use to measure distance. Miles is certainly one that we are very commonly familiar with. Kilometers is another one. Not as familiar with, but still commonly used. Feet, inches, centimeters. Making sure that you use the right units when you're talking about distance is important because it makes it more understandable. Now, distance is the length of a path between 2 points, and that path doesn't have to be straight. Displacement, on the other hand, which we're about to talk about here next, is a little bit more specific, okay? So one, displacement has a direction component to it. So this means when you're trying to describe a displacement of an object, you need to tell which way that object was moving, okay? That's the direction part. And two, displacement also is the distance between 2 points, but it's in a straight line. Okay, so imagine again that you are starting at your house and you're going to school. And unless you're walking to school, or even if you are walking to school, you probably aren't going to go in a straight line from your house to school, right? Straight line. You're probably going to have to go one way and then turn and go this way for a bit and then turn and go that way, and eventually you'll get to school. But there's some curves you got to take. That's a distance. Displacement would be, where's your house? Where did you start? Where's the school? Where did you end? And in a straight line from your house to school, how far is it and what direction is it in? That's a displacement. Okay? Doesn't matter all the curves and stuff you took. It'd be like if you could just like fly straight there or just like walk straight through walls and stuff. How far did you go and what direction? That's your displacement. So displacement is a little bit weirder, but at the same time, it has a lot more helpful implications, which we'll learn more about later in this course. All right, now, again, another example is like when you're giving directions to somebody. A lot of times when we give directions to people, we don't give distances, we give displacements. Okay, now, a displacement includes a distance, but it also includes a direction. So, if someone, for example, were new in your town and they're like, oh man, I'm really hungry, I could really use some lunch. Is there any good place to eat around here? You might be like, oh yeah, we have a Subway in town and stuff. And they go, oh, cool, well, how do I get there? Just go about 5 blocks. Which way? Right? I could walk 5 blocks that way and not end up at Subway. Or I could walk 5 blocks that way and maybe end up at Subway, but, I could walk 5 blocks in any direction. I have no idea if that's going to get me to Subway. Versus going, oh, yeah, sure. Okay, you're going to go 3 blocks east and then take a left and you're going to go 2 blocks north. Oh, okay. Now, as soon as you incorporate that direction part where you tell them go east, go north, that's a displacement. As well as, those would be in straight lines, right? You can go 3 blocks east, straight line. 2 blocks north, straight line. That's a displacement. So you guys actually use displacements quite a bit in your everyday lives. You just never really thought about it before. You maybe didn't realize what it was. Okay? Okay. Now, the cool thing with displacements is that they're a lot easier to do math with, which, of course, math and science go hand in hand, so we're going to be doing a lot of math and calculations in this course. And so we're going to talk about displacement here. Now, displacement is something that's known as a vector, okay? A vector is basically just a very fancy way of saying an arrow, okay? Vectors, or arrows, are a quantity, so that there's a number or an amount that have a size or a magnitude and a direction. So again, it's an arrow, right, that points a certain way and has a certain length to it, which is representing usually a distance or an amount or some number is usually attached to it. And because these are vectors, we can do something called vector addition, which means when we have a lot of them, we can add them together and do some math to make things a lot easier on us. So we're going to talk here about vector addition and what we can do with multiple displacement vectors by adding them together. So here's an example of 2 cars. We have a red car and an orange car. Both of them have a displacement because they're both a straight line arrow pointing and has a length to it. And they're both traveling in the same direction. Okay? So what we can do is we could simplify these vectors down, these displacements down, because they're both pointing in the same direction. We can add them together. So what we could ask ourselves is, what is the total displacement from both of these cars? Well, we have 4 kilometers going to the right. We have another 3 kilometers going to the right. If we add these together, our total displacement would be 7 kilometers going to the right, or also known as our resultant displacement, okay, where we get a result. We add these vectors together, we get a result. Likewise, if we have vectors that are in opposite directions, rather than adding them together, we would subtract them from each other. So again, let's say we have the red car going 7 kilometers right, and we have the orange car going 3 kilometers right. We might ask, well, what's the resultant displacement of both of these cars, or what's the total displacement of both of these cars? We would subtract them from each other, and we'd end up with 4 kilometers going to the right. Okay? And the reason to be going to the right is because of these two vectors, the 7 kilometer vector was larger. Therefore, when we subtract the two, that's the one that's going to be left over. Okay. Now, again, there's some math that we're going to deal with more with displacement we get further into this course. But right now, understanding what displacement is and how it works is going to be helpful. All right, now the tricky part with displacement, and the part that does maybe take a little bit more practice, is when you have vectors or multiple displacements that are not pointing in the same direction or opposite directions, but they're like at right angles. So we got maybe one going this way and one going that way. Then what do? Well, we can actually still add them together, but we're just not going to add them together the same way you would add together, the way we did before. We just take this one plus that one, you put them together, bam. So when we have two vectors or displacements that are at right angles to each other, we can still get a resultant vector or a total displacement by adding them together, but rather than adding them just straight up together, like 2 plus 2, we have to do the Pythagorean theorem. Okay, so what we're going to do is we're going to find any vectors that are in the same direction and that are equal in size, or not equal in size, but in the same direction. We're going to add them together. Any that are in opposite directions, we're going to subtract them from each other. And when we're done and we simplify this down, we should have a triangle, right? We'll have one vector pointing north. We'll have one vector pointing east. And the resultant displacement or the resultant vector is going to be the hypotenuse. From this starting point to this ending point, how far did this object move and in what direction? Okay, and all we do is, do square root of a squared plus square root of b squared equals c. So in this example shown here, we have 6 kilometers going north, 2 kilometers going north. Since those are both in the same direction, we could add those together to get one big vector that's 8 kilometers going north. Then we have this 6 kilometers going east, and there are no other vectors going east, and there's no other vectors going west. So basically, we'd be left with an 8 kilometer north vector and a 6 kilometer east vector. And then we'd have a hypotenuse as this black line, which would be our resultant vector. And we just needed to do square root of a squared plus b squared. And we could then determine what is the displacement of this object from start to finish and what direction did it travel in. Okay, so anyway, so that is it for this section of notes. Again, there are some practice problems, and I have a video of me going over those. So if you need more help or you're confused, go watch that. It will definitely help you. Okay, but otherwise, as always, if you need any other help or have questions, reach out to me. You can email me, talk to me in person. We could always do some tutoring over a Google Meet or something, but make sure you get the help you need. All right, guys, I'm Mr. B. That's it for this one. See you in the next one. Bye.